Enlightenment and Enlightenment thinking in general. Mind you, periodization here is always an issue. Several of you found that if you Google, you'll find various periodizations for the scientific revolution as well, extending this phenomenon until the 19th century. Yeah, if you want to call the revolution and you stretch it over more than one century, you become even less trustworthy, I'd say. But there are indeed various ways of delineating these phenomena. Usually in present day historical literature, the late 17th and the 18th century are dubbed Enlightenment. And in some books you'll find that Enlightenment is also stretched well into the 19th century. Enlightenment thinking, mind you, is in various ways very much recognizable. Some Enlightenment thinking, and that's what I want to stress here today. The standard view, just coming back to the standard view so now and then, is that there were the Dark Ages, then the Scientific Revolution, and then finally Enlightenment came, and all of us were becoming reasonable human beings. Yeah, thinking that the state and the state is there to serve the people, and the church should be completely separate from the state. This is both very Eurocentric and not completely true, even within Europe. I will say it's barely true. Yes, this idea did exist, and yes, this idea did end in the, this idea died, I would almost say, in the French Revolution at the end of the 18th century. Yeah, with the French Revolution, that was the first time that these new ideas about state for the people were put to the test and failed miserably. And after a few years of revolution in the 19th century, the monarchs returned and restoration came across to be democratized only in 1848. So the standard view is not completely and utterly true. The picture that you see here is Isaac Newton, of course, in an elegant pose for a book, in front of a book, in front of a globe, sitting comfortably, leaning back in a chair, doing science. Mind you, Newton was one of these people who didn't have to be paid to do science. And his science was very, very multifaceted. So let's have a look at what science meant in the 18th century. There were there were various places where science was configured. And one of the things that is striking in both late 17th and early 18th century is the rise of learned societies. Here's a learned society of gentlemen joined together to be taught together in mathematics, physics, everything new that could be there to know. In the syllabus you may read about the example of the Royal Society, so that were the court mathematicians that were joined with other courtiers. So they, that was even more posh than this one, but you can see these are rich people. Striking examples of the late 17th century are people of lower standing. Well, you can see from the Whigs that they were not completely poor, but this is a pub. People gathering in a pub doing, in this case, drawing together. They make pictures. This is a society who marvel at the art of painting. And as you may have read in the syllabus, there were also societies that marveled at the beauty of mathematics. And they also came together in a pub, had a drink together, posed problems to each other, and went along doing mathematics. Okay, so these are the two, so to speak, extremes of the Mathesis Universalis and the mathematical arts traditions. Both of them gather and make make their subject something to be shared, something to be marveled at together. So now then, in Enlightenment, what was mathematics? It was indeed this Materia Universalis that you've read about. I'll just have you make you have a look at two books. The Principia by Newton. Note that there are no formulae, note that there are no vectors, note that there are no here. It's an English edition, a re-edition. So yeah, you can see that. And here, slightly earlier, a Mathesios Universalis book by several people, written by several people. So there are 4 books bound together in one volume here. Someone was stabbed over it, so you have some stains here. But yeah, it's a completely different book. Browse and see how completely not recognizable this is as mathematics. Although some parts may look a little more like our mathematics, it is not our mathematics. It's in Latin, that's one problem of course, but even if it's in English, you'll note it's text. It is text. It doesn't resemble mathematics. That's Mathesius Universalis. Both of these are examples of Mathesius Universalis. And the other part of the spectrum of mathematical ideas, mathematical worlds in the 17th, 18th century is the practice of bookkeeping, surveying, copying, the ideas of mathematical arts. So, when it was Enlightenment, I already discussed that before. Yeah, you can stretch it from the late 16th until the late 19th century. I confine it to the time frame. Let's see. Yeah, I confine it to the time frame of 1648, which is a convenient date because that's the date that the peace treaty for the 8 Years' War was finally signed by all parties involved. Until 1795, which is the date, or 1794, which is the date that the French Revolution broke out. So, the people you see here are the seven laws that govern the United East Indian Company that were to send out ships to East India, part of the Netherlands, in the 17th century. This is a picture from the early 18th century where they convene and have a nice chat together about what to do with the next trade route, how to slaughter more enemy ships and how to make sure that profits stay up tuned. That's what they did. And note the globe and the large pile of books and atlases that are in front of them. That is their devotion to the mathematical arts or to the Mathesius Universalis, whatever you wish. They show that they know their math. That's what they do. They indulge in it. 1648, 1795, as I said. That's more or less the time. These dates should not be taken too fixed. Yeah? Don't bother too much about it. They are big dates that are convenient, years that are convenient to me. And yeah, you have to put an end somewhere, you have to put a beginning somewhere. That's the idea of that time frame, the idea of Enlightenment was the mathematical spirit, the esprit géométrique, it was called by Bernard de Fontenelle. Geometry was a practical subject, in surveying, in painting, in gardening, but, and this is an important but, Euclid was a great example of describing understanding of why things work. And then many people thought so. Many people tried to imitate Euclid's way of reasoning. That was, and you can see that in various examples that are mentioned in the syllabus, and then I'll show some other examples here today. This started, if you want to call it, started. But one of the first people to actually focus on this idea is Descartes. So slightly earlier than 1648, it's 1637 already in his Discours de la Méthode, where he writes on geometry and tells us that, well, geometry is by far the easiest because all you need is a sensible set of models, and everybody agrees that his are working perfectly, so that'll do. That's all that you really need to do geometry with. And Bernard de Fontenelle then, in the end of the 17th century, epitomizes it by saying that you don't really need to know geometry itself to profit from its beneficial effects. If you just suck up the spirit of geometry, that will do. And that's what many of the people will be doing. Yeah? That's the examples that you will read about in the syllabus, and the examples that I'll show today are partly people who have sucked up the spirit of geometry and who don't know much about geometry itself. But two books going around, so Newton and the Descartes book, are both people who knew their geometry and their mathematics very well, in the way we understand it even. Okay, here is Descartes. The man on the right is Descartes, and the woman in the middle is Christina of Schwerin, princess that Descartes was teaching. So he's teaching her mathematics, and here again, a celestial globe showing that devotion to mathematics. In La Géométrie, superficially, Descartes only links subjects of algebra and geometry together by showing that you can multiply lines, thereby obtaining another line, not necessarily the surface of an area. Yeah, the usual interpretation of multiplication of lines was you determine the area of a rectangle, which does make sense. Yeah, you multiply two lines and you get a rectangle. That works. And Descartes shows, well, it's not that strict. We don't need to get ourselves on dimensional problems. We can multiply more than 3 numbers, that is. If you think that multiplication yields a rectangle, then multiplication of 3 numbers, yeah, that you can still do that, but multiplying 4 numbers becomes difficult. Well, Descartes says we can still do that. There's nothing wrong with algebra. There's no reason to doubt algebra because we can simply choose a unit length and show that indeed by similarity of triangles, that the result of multiplication can be a line segment itself. It's as simple as that. That's what he showed. But he shows much more deeper things than just that. Yes, within mathematics, this is the idea that's picked up, and I'll give some examples of it momentarily. But the more important idea that he provokes with this geometry is that all you need is a good set of models, and you can do mathematics, you can reason. And reasoning is a powerful tool in science. Okay. One of the things that his work yields in mathematical sense is the whole field of construction of equations. Yeah, because, yeah, sure, we have algebra, which is a subject that was popular among the mathematical artisans. You have geometry, which was the subject popular within the academic culture. The two didn't really fit together. They couldn't really fit together. The geometry, the people preferring geometry, they try to frame every theorem within algebra in geometrical terms. Newton does, you can see, he makes it into language and into a picture. That's what Newton does. He doesn't use, he restrains from algebra completely. He doesn't trust it. Whereas the algebraists, well, they like to do their algebraic tricks. And Descartes shows, well, we're not really that different. We can translate one into the other if we just know how to interpret the formula. And one way to to show that every formula actually has geometrical meaning is by constructing a machine that draws that creates the geometrical curve that fits the formula. So what you see here is a machine that can actually draw a 4th degree polynomial. And you can create machines that draw 5th degree polynomials, 6th degree, 3rd and 2nd of course as well, but 2nd is easy. On top you see one that draws one of 2nd degree, that's an ellipsis. The ideas are simple. You need to be able to construct the thing, the formula, before you can trust that it actually represents something sensibly in geometry. And this field remained in existence until the beginning of the 18th century. It's completely in oblivion today. Nobody constructs functions anymore. No, it's completely useless. But it's set in motion by Descartes, by showing that, indeed, geometry and algebra are not that far apart. We can translate geometry, we can translate every sensible equation into geometrical, sensible objects. Now, well, then you show that you can. The book in vellum that's going around is, in fact, one of these attempts. It shows that you can construct, with every equation, you can construct a machine that does the trick. With Isaac Newton, you see that most notably. Yes, indeed, he refrains from doing algebra, so he's one of these old-fashioned guys who doesn't want to go into algebra. He doesn't want, of course, he was British, and Descartes was French. Why trust someone from France? They were in Brexit before they entered the Union. That's simply the way that the British were, and that's the way that the British still are. He's very thoroughly believing in the Cartesian idea of using your models, though. He is constructing in Book 3, as you may see, he is in Book 3 constructing, on the basis of his 3 principles. In the English translation, they are translated by laws. That is because this is a rather late English translation. Original, it says principles, not laws. Laws are of course the things that are made up by God or by the king, and not by a mere mathematician, not even by Newton, who was knighted in 1705. But so he was formulating principles, and on the basis of these 3 principles, he shows how our solar system actually works. He just shows us that it's a great chapter. It's completely in prose, no formulae, a lot of pictures, but if you go into the details, if you read it, it's actually quite astonishing what he does. He really does. What he doesn't do, which is quite remarkable, he doesn't ask the question, because that wasn't the question for him, is this solar system stable? Which does become a question in around 1800. Does it stay evolving around the sun? Or will it collapse someday? Or will the planets collapse? Will they? It's quite a simple question that we would ask ourselves as soon as you realize that you can calculate such things. But he didn't ask him that. He didn't ask that for one moment. It occurred to him that it could be an interesting problem. Of course it was stable. God created it, right? And that's exactly where the limits of enlightenment are. That's where his prejudices were. He was looking at creation. He was describing creation. There was no problem with stability. That was, no. It was nice that he could describe it. And by this description, come close to the 3 principles that God must have used to devise this system. Moreover, what you also forget is that, or what you tend to forget easily, is that Newton was also involved in finding the philosopher's stone. And that he was involved in the mint, the royal mint. He was the one trying to catch all people who were on all kind of sleazy ways, trying to make use of the money system in the UK, in London, mostly. He was doing very practical things just as well as his Principia. He wrote on various alchemical works just as well as this. So this is the recognizable part that we still love. And the other things we don't read about anymore simply because they don't come close to us and they don't fit our picture of Enlightenment thinking. But it fitted his ideas of Enlightenment thinking, definitely did. So keep that in mind. And that goes for everyone in the 17th and 18th century. Comparing, this is of course changing, slowly changing. Compare this to Euler, end of the 18th century. Now we're end of the 18th century. Compare this to Euler. He also, you could call him a court mathematician, was part of the St. Petersburg and the Berlin Academy of Sciences. Never became the president of the academy, which he resented, but that was because he was from lower social standing and clumsy in his communications at the court, which is kind of a pity. He was a great mathematician, published wonderful things, yet at the court he didn't really fit in. He was the odd one out between the learned philosophers that mocked him. But, did he write about the Philosopher's Stone? No, he didn't. His mathematics is much more recognizable to our view, to our eyes, than is Newton's, which is not even a century older. So what Enlightenment thinking, if you believe in progress, then here it is, Newton to Euler. Newton's still very much involved in alchemy, Euler, no longer. Was Euler then the modern mathematician? No, he wasn't. He was involved in, for example, building fountains for the court at, at one of the courts where he worked. not in Berlin, I think at St. Petersburg, but at least he was working at fountains. And made his mistakes there as well. He was not that good in constructing fountains, or, as is usually the case, the man who should do the building work was not as good in his work and used inferior materials. Notice the similarity with the Stephen story, so Euler was doing various things as well. He was not the present-day mathematician that we know. He was not paid to do mathematics. No, he was kind of a courtier. But his mathematics has become much more recognizable as our mathematics. His algebra textbook is readable as a present-day algebra textbook. So it's Enlightenment, that's some kind of progress. Enlightenment thinking does come close in several senses. And what I want to stress is it doesn't come close in various senses as well. Let's have a look at other Enlightenment thinkers, the ones who are more remote from us, the gardeners. The gardeners who were part of the court, at least if they were successful gardeners, most of them were not, of course, but if they were successful gardeners, they were part of the court, and they could they presented themselves as mathematicians, like the painters. In the syllabus I've been quite elaborate on the painters. Here I'll expand a little bit more on the gardeners and see how that works. This is a picture from a gardening textbook. A lot of gardening textbooks appeared in the 17th and 18th century. A remarkable number of them. And all of them written by people who present themselves as mathematicians. Mathematicians, mostly as mathematicians and gardener of, and then some kind of court, minor or major, is following. If you have never seen it before, please visit the gardens of Versailles if you have the chance. And then you will see what kind of gardens we are talking about here. That's the kind of garden. Straight lines, large fountains, big works, nicely trimmed hedges, everything, fine and in order. Straight lines. For some reason, straight lines and circles were popular. With the garden, with his garden, the king could show his mastery over creation. I'm the Lord here, look at my garden, I have it under control. Perhaps the people outside are rebelling, but my garden is under control. So That was kind of what they wanted to show with that. And the mathematician had to help there. Here is a picture drawn by Knoop, one of the German gardeners of the early 18th century. He designed the gardens for the Duke of Brunswick and for the Duchess of Friesland, here in the north of the Netherlands. And in that later capacity, he was even acting as a courtier, was adopted at the court, and functioned there for several years, redesigning the gardens completely, publishing a lot of textbooks on mathematics while doing that. And well, apparently he drank a lot and was a little too courteous to the women at the court, and was expelled after a few years for open drunkenness and irrespectful behavior. But that's the sad part of the story. The happy part is that he was making a lot of social progress here with help of his mathematics. Well, what did the mathematics entail then, apart from designing the garden? You can imagine that, well, it takes some surveying skills to lay out the garden, but what else? Well, yeah, not much else really. Not much else, to the honest eye. But let's have a look at his textbooks on gardening. What was his gardening book about? That was Euclidean style, phrased Euclidean style, so this is the mathematical spirit that de Fontenelle was talking about. Euclidean style phrased, talking about what is beautiful to the eye. So the beauty is defined, and the way that we should look at that beauty is defined in terms of axioms, theorems, and proofs. It looks odd, it is odd, but it worked. It worked for him, and it worked for other gardeners. People designed their gardens according to geometrical principles. A circle there, straight lines there, trimmed hedges at the sides, and trees at the occasional places. And it went even further. This is a picture from one of his textbooks as well, from Knoop's textbook. He goes into describing several types of fruit, several types of apples on this page. He has pages filled with these kind of drawings. See how much love goes into these pictures, yeah? They have really been, he really went into painting. Well, of course he didn't paint them himself, he had some little child paintings and then slash a bit around it if the paintings were not that beautiful, but love goes into these pictures. He is very much in contact with his topic. So yeah, compare several types, several species of apples. That's what he describes. A whole book called the Pomologia, so the learning of apples, describing a great number of apple races, and all of them, well, are to be positioned in specific places in your garden, according to mathematical principles. But the way that these apples are organized is mathematical in essence as well. That's mathematics to him. That's his view of geometrical ordering. And mind you, he's not the only one doing this. Linnaeus, at the very same time, late 18th century, a little later than he, Linnaeus does the same with his systematic description of animals. Kingdom of animals, where you have the fishes, the lizards, mammals, etc., and subdivisions from there. So that's the very same mathematical organization that is attempted, both here and with Linnaeus, trying to describe nature. So here you see a completely different picture of Enlightenment thinking projected on gardening and organizing the garden, describing the garden and describing what's in it, organizing what's in it. It's another way of Enlightenment thinking, not the one we usually see. Here's another one. The mathematical societies. I have two books to go with that as well. Just to have an idea, mathematical societies end of the 17th, early 18th century. Simon Panzer. This is a mathematical oddity chamber, as oddity chambers were abundant in early 17th century rich people's environments. The mathematical oddity chamber shows us what kind of weird stuff you can solve with algebra. And that's what Simon Panzer does. And that's early 18th century. Later in the 18th century, 70s, 80s, is this beautifully colored picture book with a lot of text by Hooper, Mathematical Recreations, or Rational Recreations, but using the principles of numbers and natural philosophy. So have a look. There's love in this book. This is beautiful. Both of them are. They are various expressions, different expressions of what mathematics should be about. And in this picture there is that very same expression of what mathematics should be about. These mathematical societies, small scale, people within the pub, as you saw in the picture just a couple of slides before, these people went to the pub and they had a jolly good time together, posed each other problems, had a peek at this mathematical oddity chamber, or marveled at the peculiar things that nature had to offer. What you need to do here is have a look at these pictures, so you see you can hold them out, read the text with it. It's great stuff. That's another part of society where enlightenment thinking was taking place. What do they think that mathematics is about? This is the Amsterdam Mathematical Society, by the way, founded in 1778. Here in Amsterdam, as you may guess, they think that mathematics is about architecture. That's represented here by a huge pillar. By surveying, that's represented there by the surveyor's chain that's wrapped around this pillar, and by several sticks and other measuring instruments. Navigation, that's represented by that machine there on the left. Globe, map making. A telescope, a ship, also for navigation, of course. A hauling instrument on the top or on the bottom of the pedestal. A pyramid with people climbing on it. That's representing the effort that it takes to become a real good mathematician. And then in the right-hand corner, the right-hand lower corner, there's a small pile of books. And which are the names of the books you probably can't read, but it's Stevin, Dutch, of course, Stevin. It's Newton, it's Huygens, and de Graaf, which I will leave out here. But that's the kind of people that are on the deck. The books are only a very, very small part of what mathematics is really about here, as you may see in this picture. That's great. Here's another picture from a kind of book of these. They had these mathematical recreation books printed and marveled at. That's what they did. Here's another picture from a similar book. And they tried to find answers to questions from Roman law. That had always, of course, been the field of the lawyer. And so now and then you could find these similar questions in these textbooks on arithmetic of the early 16th century, but they were hardly ever taken very seriously. Here in the 18th century, within the societies, they were taken up as a personal way of showing that you know your mathematics. Well, we know how to solve this. One of the peculiar questions, for example, was the question of a inheritance taking place. A man who dies, leaving the pregnant woman, decides that his fortune is divided between the woman and the child where the woman receives one part of the fortune and the child 2 parts. If the boy happens to be a man, and well, these were different times than today. If the child happens to be a girl, then the mother gets twice the fortune, twice 2 parts of the money, and the child only 1. Yeah, and then what happens? A twin is born, and one seems to be female and one male. What to do? Yeah, and you can make that into a mathematical question, and several mathematicians did, but it really isn't a mathematical question. The problem has not been, does not compute, we would say. Does not compute. You need more information, but you can, of course, start doing some arithmetic and figure out various ways of how to divide the money. You can. Anyway, these kind of questions, that's the kind of questions you may see posed in these pubs. That's the kind of things that they were wondering about. That was the kind of things they were marveling about. That was the ego boosting that was taking place. So some people actually understood that this question could not be solved unless you get some more information. You have to make a decision. It was the decision of a lawyer. And that kind of stuff. That was enlightenment as well. Ego boosting in the pub about mathematics or about physics, which can be great. And then the last one that I want to address is politics. In haste, I copied a couple of slides from another presentation, but I wanted to show you as an example of thinking of using mathematics in politics. Let's be frank and let's be simple. Politics was not a mathematical subject. It wasn't. But a lot of important people, kings, princes, burgomasters, counts, whatever, were very much in favor of mathematics. The burgomaster of Amsterdam here, Johannes Hudde, was an important mathematician as well. Huygens was a very famous diplomat and an important mathematician, we would say today. Yeah? They didn't like to be called mathematicians, but the work they did, the work that they showed, the publications they made, were mathematical. In the syllabus you'll have this example of the moral algebra, which I will not go into detail with, but just to show you that that was not standing on itself, I'll have you handing around a arithmétique morale by the Comte de Buffon. This part of the book. Yeah, you do arithmetic on morality. Moral decisions can be computed. Well, can they? Well, according to several people, you could. Could you in any case? No, you couldn't. And here is an important example that would indeed help to illustrate that case. We're talking late 17th century here, 1670. Then Huygens had published a book on calculating of chances. And it was a book copying the style of Euclid, so again, more of a geometry, according to the mathematical spirits. It was a book published according to, it resembled Euclid's style. It didn't calculate chances. It didn't even use the word chance, not in its present day form. It merely stated that this situation in the game is worth as much to me as this situation in the game. So, for example, in throwing a dice, betting on that the dice throws 2 will be as much worth to me as betting that the dice will throw 6. That's the kind of statements that you will find in Huygens' book. And he does quite a good thing there. On the basis of that book and a book by John Grant, he starts a discussion with his brother. Grant published the Bills of Mortality, which was kind of a weird thing. London, 16th, 17th century. Yeah. bills of mortality were collected every day. And on that bill was stated what was the cause of death of a man or woman who had died. If the cause of death was the plague, then people knew, okay, we have to get out of the city and be safe. That was the idea. Containment policy, you could say. And that's in the late 17th century. So it was Wuhan before Wuhan was infested. Yeah, that's how they did things in the late 17th century. On the basis of these books, John Grant had devised a table of mortality. He says, let's see. In general, if no odd things happen, in general, of 100 people who are conceived, of 100 people who are born, after 6 years, after 6 years, 64 are still alive. You can imagine child deaths were quite occurring quite often. That's also why most people didn't give their child a name until, well, they were 6 years old. Really, that was the moment that you could actually name your child. Please. Yeah. And he had devised this table. On the basis of this table and the theory that was set out by Huygens, the brother of Huygens, Lodewijk, Louis, said, hey, see that? We are both, we are both about 46. The chances that we will become 61 years old are about equal. So, well, he didn't use the word chance. That's the point. That's the point, really, sorry. Yeah, he said, just calculate your odds of the 10. Yeah, you are 46 now. I can bet safely, that's as much worth to me that you'll become 61 as that you will not become 61. 61 is your vantage point. That's where your losses are gained. That was his idea. And yeah, the calculation is simply done. And Christian receives this letter and sends a letter back saying, wait a minute. How can you say that? By 66, only 3 of these 10 are left. So that's far less than half. Okay, that's 66, but if I interpolate, at 61 there will be 4 of us left. That's also less than 10. That will not be an equal bet. That will never be an equal bet. So don't place that bet. This is not, 61 is not the point where you have equal opportunities. And then, but Lodewijk insists, but this is the basis of your calculation. What's going wrong there? What is going on there? Let's see, what if we take one of these babies who's just recently been born? What bet do I place on his age that it becomes fairly even whether I bet that he's going to reach that age or that he's not going to reach that age? Well, if you do math, it turns out to be 18 years approximately. Yeah, so someone who's this first 36 that die approximately at the age of 3. So that's the way that the calculation is done. It's quite elementary, right? And then Christian comes with he comes with a table that's not from Grant, but that's made up. And he makes it up. He makes up this thing as just as it fits his argument. And this is remarkable, fitting your table to an argument. So he says, well, just suppose, for argument's sake, that I have the following life table. Of 100 that are conceived, there are only 10 that remain alive after 6 years. So most of the people die. But these 10 people, they become really, really, really old, right? According to your calculations, yeah, it's a safe bet to say that someone who's just been born will become 18 years or will not become 18 years. Well, here you see a typical example of that. Don't place that bet because you have a 90% chance that you'll lose that bet. What you see here is the difference between the median and the average number of things that are being calculated, right? That's the median being sometimes very much to the left or to the right of your average number. But the most important thing here, that's what the brothers find out eventually, but the most important thing here is that there is a life table constructed for argument's sake, which is peculiar to say the least. Yeah? And does this in any way come close to political thinking of Benjamin Franklin, whose moral algebra is described in the syllabus, which I will leave here for now? Well, in a sense it does. But where with Huygens this was part of a personal letter exchange between people, between two brothers in high places, with Benjamin Franklin has become part of general political culture. Mathematics was important at the end of the 18th century. Thank you for your attention and see you next week.